Well, good morning. Hope everybody had an easy time finding the place. I was surprised to find out how big PayPal had become in the last 20 years since I was at PayPal in their other campus in San Jose. And first, I guess since we're the opening talk, I think maybe we should give a round of applause loud enough so the people out there that set this up and the people at PayPal can hear that we're really happy that they volunteered this wonderful facility. So let's give it up for them. Okay, that should suck some more people in too. So you guys did your job. I'm Jerry Kurata, as you can't tell by the little picture there, when my hair was a little darker than it is now, but not that long ago. Let me ask you guys a question. Obviously, this is talk about TensorFlow and deep learning, and we'll even talk about something called Keras if you're not familiar with that. How many people are familiar with deep learning? Okay. How many people are here mostly for the TensorFlow part of the talk? All right, for the TensorFlow people, how many are here because it's a good way to get a really good paying job? Be honest. Okay, yeah. It happens to be, we'll talk a little bit about it. I'm not going to go too deep into, we're going to actually code because this says code camp, but I'm not going to go too deep into the code. So you're still going to have to go to tensorflow.org if you want to get really into it, or you can watch my Pluralsight course. So on that. Anyway.
Where is the course?
I have one on pluralsight.com. Pluralsight. Pluralsight. Who said that? Okay. Here, 3-month subscription. I have some, and we have a couple of people from Pluralsight over on the side here, and if I run out, you know, I'll throw these out from time to time for good questions. Let's keep this interactive. Let's keep this light. If I run out, though, there are a couple of people over there from the sales organization that have, I saw they had huge stacks of them, so get there early to get the free month subscription. All right, so let's get started. You know, deep learning is one of those technologies that has been kicking around for a long time. Deep learning and its base technology, neural networks, have been around since the 1950s. And back then, computers were a little slower than ours are now, surprisingly. I mean, these guys were doing some of these things with kilobytes of memory and a whopping maybe like, 8 to 10 megabytes hard drive that was about the size of your washing machine. So it's pretty amazing when we start to go through this just what they could achieve. Now, the reason deep learning has become so popular is what? Okay, throw it out. Artificial intelligence, right? We now live in the age of artificial intelligence. And because of all this horsepower and these good algorithms, we're now able to create artificial intelligence systems. You can't go to a web page today without seeing 10 articles screaming, XYZ company is using AI in their new whatever widget they're building tomorrow. And of course, then there's the poster child for AI, right? Autonomous cars. Now, this particular car is not meant to push any particular brand name or anything like that. It's not meant to push the folks up in Fremont or anything like that we really love, though, right? We'd all like to have this. And no, based on my joke earlier, we're really not raffling one of these off today. So if you came for that, too bad. But autonomous cars are great. I mean, does anybody else here commute in the Silicon Valley and in this area? I'm sure. Wouldn't you love to be able to flip a switch and just say, drive me to work? Or the holiday shopping season is coming up. Wouldn't you love to have it drop you off at the mall, flip a switch and say, you go park yourself and hunt around for that spot, for an hour and a half. And come get me then when I push the other button and come get. Well, that's where we're getting to with this technology. And this is transformative. In fact, Andrew Nag, people know who Andrew Nag is? Familiar with Coursera, Stanford professor, was former head of Baidu AI, was one of the founding members of Google's Brain team, things like that. He calls AI the new electricity. And the reason he does that is because, like electricity, artificial intelligence is going to change the way things are done in all sorts of businesses. There's going to be a distinct difference, kind of the before picture and the after picture. And if we think more to the internet, it would be very similar to that, right? How many of us, when we buy something, don't hop on the internet and take a look before we go down to a store, right? Before we used to go down to a store, they had 3 items for sale. Now we go onto Amazon and there's 50 of the same version of things. We read the reviews, we'd sit, and we pick the ones on the first page because that's how the internet works. But before we get too far, let's define some terms here. This is kind of the one I like for artificial intelligence. Maybe you have your own. But what I like about this definition is this part, that it gives us a way to determine if something is artificial intelligence. Namely, if we assume that it would normally require human intelligence to do it, we can say it's now artificial intelligence. Now, what's the downside of that? Anybody have any thoughts? The change. Well, jobs too, we can talk about that offline. But the change, because this is essentially a moving target, right? Remember when systems first came out? Humans only can play grandmaster level chess. 20 years ago, that got wiped away. Humans only can play Go. Last year, AlphaGo beat the world champion in Go. Humans only can create art. Now we have generative adversarial networks that create their own art. So we have this moving, if you will, barrier that we have to cross before we call something artificial intelligence. So that brings up the question, what then gives artificial intelligence its smarts? Well, that comes from machine learning. And machine learning is something that learns without being explicitly programmed. That doesn't mean we should all just leave here because we're not going to have any work in the future. What that means is we need to learn a different paradigm for developing these systems and teaching them how to be smart. And let's take a look then and see how that's fixed back with our autonomous car. Imagine this is the artificial intelligence that powers our autonomous car. We have various things in it. We might have sensors. We might have radars, lidars, cameras, what have you not. Those can gather up information and ship it off to something that we'll define in a moment that gives it the intelligence on what to do. What do I do when I see a piece of paper in front of me? Probably not a whole lot. What do I see when a ball bounces in front of me? Maybe that's something different, because what follows a ball bouncing out in the street? Kids, exactly. So maybe we ought to slow up. So how do we do that then? This smarts, if you will, for the artificial intelligence system would say, all right, talk to one of your controls that controls the speed and the brakes and slow down. Make sense? Okay, what is that intelligence then? As we just talked about, that intelligence comes from machine learning. And the field of machine learning has dozens of algorithms, maybe hundreds. But the ones we're concerned with in most autonomous cars and various other systems that give us the very, very intelligent behavior are neural networks. How many have heard about neural networks? Okay, great. We're going to look at neural networks today, and we're going to specifically look at deep neural networks. Okay, in fact, let's take a look at one right now. Here's a neural network. On the left, we have various inputs coming in, and these get passed to these neurons. Neurons are like a mathematical attempt to develop the neurons that are in your brain. And I would not push that analogy any further than that because they are mathematical structures. Two terms that you'll hear with respect to neurons is a weight and a bias. And we'll talk about that in a minute, but those are what make the various neurons determine whether they're going to pass the signal on or they're not going to pass the signal on to the next layer of neurons. Now, notice the dot, dot, dot. Oh, by the way, these are called layers, these vertical stacks of these. Notice the dot, 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 though, here. When we talk about a deep neural network, it's based on how many hidden layers we have. If we have 2 or 1, it's just a regular old neural network. If it's more than 2, we call it a deep neural network. It's just a way to distinguish between the two, because typically complexity from computation, you know, if you have a couple of layers, you can probably do that on your Mac, like I have here. If you have 1,000 of these things running off, and each one of these has maybe 10,000 to 1 million neurons, you're not going to do that on your laptop computer unless you have a lot of patience. So you're just not going to. It's not unusual for a deep neural network, when it trains against data, to run for 1 week, 2 weeks, 3 weeks, or 4 weeks. And I'm talking big clusters at Google when they build their translation engine. They're running for a long time. Okay, so anyway, once we finally, let's go back. Sorry. Once we finally get through all these hidden layers, we have to output. And a lot of times the output, and we'll see that today, is a probability. So we may say, this is a cat, or this is a dog, or this is an aardvark. And we'll get a probability. Looking at a picture, we may say, oh, it's 60% a cat, 20% a dog, and 10% an aardvark. I'm not sure if that's correct, but anyway, you get the general idea. And to ground this, let's look at some input data then. This is something called the minced digits here. And minced is, or MNIST is probably the correct way to pronounce it, is for the modified NIST data set. This is from the 60s and 70s. NIST is the National Institute of Standard and Technologies. These have been modified by lowly grad students to go through and look at 55,000 of these. Isn't grad school wonderful? I loved it so much. Anyway, so some poor grad students had to go look through 55,000 plus. Oh, I take it back, 75,000, because there's 55,000 in the training set, 10,000 in the test set. And you keep those separate. They had to look through these and say, yeah, that's a 3, that's an 8, that's a 6, things you do to get a PhD or a master's degree. But look at this data, and let's just talk just a little bit about what it would take to program this by hand. So let's suppose we want to look at these 8s, like in the upper right-hand corner. Okay, there's an example. Okay, I got it. An 8 has 2 circles, and they're kind of like tilted off to the right, and we never lift our pin when we go up and down, so it's a contiguous thing, right? Perfect description. I can write that in 45 lines of C++ code. All right, well, let's run this one through it. Is that an 8? Everybody agrees it is, right? It's got that thing, it goes up, yeah, it's tilted, but what's this little thing? Okay. We put an or statement in, or it can have a little thingy hanging off to the right. Okay. All right, how about this 8? Well, it goes round and round. Oh, wait, it's got a hole in it. Okay. So what I'll do is I'll put a parameter file in there, and we can have discontinuities of 7 or 8 pixels or less, right? Great, got it wired. Okay, let's look at this one. Oh, come on. This guy even lifted his pin. He just did 2 circles. What is this, a 2-year-old or something like that? All right. And what about this one? Well, it looks the same. Oh, wait, that's going off left. Well, that's a left-handed person. We don't need to worry about them. So we'll forget about them. My model and algorithm is perfect. Well, obviously it wasn't. Anybody want to guess what that is? I'm still working on that one. Okay, and what language is that, a zero? Okay. It's either ASCII or it's part of the APO programming language or something like that for the old people in the group. All right, so whatever it is what it is. But our job, we're being paid the big bucks here, is to write something that can figure these out. Well, us being smart and us being machine learning wizards, we realize that we can't do this with just regular programming, right? We're going to take those digits and put it into our neural network. And we're going to train our neural network through these. And what this training process is going to do is find out the various things associated with it and then tune these neurons to recognize them. Once again, this tuning involves adjusting weight and biases in them. So we push it through, and the weight and biases get adjusted, and cool, we're all trained. What did we train on? Well, maybe we used curvature and size, just like we were doing when we were trying to do this manually and things like that. But maybe, and in fact likely, use things that we as humans do not see, relationships we don't see between those digits. It might be, I don't know, shading, whatever. And this is the magic here with machine learning in general and neural networks specifically, is they detect things that we as humans probably do not detect. And magically, after all that happens, they can give us the probability that that thing we're feeding is a 0, 1, whatever through the night. Okay. Now, once we have that model trained, this is where you spend your weeks of time. We can then take that modified model with the weights and biases all put and shove it into whatever device we want. We can shove it onto a cell phone. I can shove it on a little chip. And now I have a little device that when it sees this digit, 5, I think that's a 5, everybody agree? Even though it has this funny little thing going on here. It goes through those weights and biases and say the highest probability number is a 5. We all cool with that? Questions? Go ahead. Yes, sir.
Yeah, two questions, which I've never understood. You need to come back with some initial value for the weight and the bias?
Yes.
Okay.
Yes.
So basically, the goal of training is to make sure that the weight and bias are going to give you the outcomes that you want, right?
Absolutely, yeah. And that's a good question. If you don't set initial values, it's like mx plus b, remember the old equation to a line? Essentially, you'll get 0 out and it'll never twin. We'll see this in a minute. I'll show you in code.
Second question.
Okay.
You didn't talk about the function in each of these neurons. So same question, how do you come up with the function in each of the
I'll show you that also in the code.
And are the functions the same in each neuron?
Each layer of neurons.
Yeah.
Yeah, that's a good question. So each of these, what he's asking about, there are internal calculations that are performed in these neurons. Each layer looks the same, okay, in general. There are special cases when they don't. But this layer right here does not have to look like this layer. And in fact, in our example, we'll see how different they can be, because it's what function you want to have happen in that layer that determines how you put those together. A little beyond where we're going to get to today, but I'll try to address it. Okay, so if you take nothing away from this talk, remember this slide. Machine learning is not done by explicitly defining the program. It's done from the data. Okay, so we're going to go to a demo in a minute, and let me quickly talk then about the various tools we're going to use. Language-wise, we're going to use Python. Python and R are the two big languages. Python is probably the biggest. The reason Python is so popular is every college student from the last 15 years probably had as their first language Python. Just is. Back when I went, I think we used Pascal or something like that. And the other Pascal knew? Okay, all right. All right, I just did an age graph based on the correlation of the first language. How many did assembler as their first? Okay, okay. Okay, binary? No. All right, so it is what it is, and deep learning has come of age in the last little bit, so all your researchers, your PhD scientists and things like that, they knew Python. So of course that's the perfect language for it, right? Whether it is or isn't. But Python is like, any other language, you can extend it with libraries. The one big library you're going to see if you're going to do machine learning of any form is something called scikit-learn, which is short for Scientific Computing Kit, and machine learning, okay? So you're going to probably have to have that in there. In fact, we'll have it today in ours. Now, the problem is scikit-learn is great for a lot of machine learning. It does great at regression, decision trees, a lot of other things, completely functional. But when it comes to deep neural networks, you have all those neurons and you have to keep track of them, and it just kind of has this really basic thing and says, here, that's enough. You go write the next 5,000 lines, right? So we want to use better deep learning frameworks. These are the big three deep learning frameworks. TensorFlow, which about 2/3 of the people raised their hand about, so I assume they know about that, heard of it, is the 800-pound gorilla. TensorFlow is free, well, they're all free, from Google, and within the last 2.5 years has gone from like no knowledge to, I think, about 60 to 70% of people doing deep learning are using TensorFlow. CNTK is Microsoft, and it actually can outperform, remember that long training time we were talking about, TensorFlow in a lot of scenarios. It also supports, in addition to Python, C#, so if you're a Microsoft person, that's a cool thing. Theano is one of the oldest frameworks, and it is still being used by a lot of companies just by virtue of its longevity and because the guys in charge of AI at certain companies love Theano because that's what they learned, just like the guys that love Python. Okay, now, we're going to do TensorFlow, and we'll see this just in a minute, that it's a little, we have to do a lot more plumbing than I personally would like. You well know good programmers are kind of lazy programmers, right? Because they write libraries, and they write the libraries so they can focus at the problem at hand. Our problem is building a great deep neural network. So, on top of TensorFlow CNTK, you can run a library called Keras. Keras uses the term backend. So you can have the same Keras code run on a TensorFlow backend, or have it run on a CNTK backend, or a Theano backend, with just very, very few modifications, maybe 5 to 10 lines of code at most up in the top. You just say, hey, I'm running over here, I'm running over here, I'm running over there. Now, there's a lot of information out there, but here's the one ad slide I have in here. I've done a number of courses on this. Get the little sticker from the Pluralsight guys. One's on machine learning in Python. There's a TensorFlow getting started. And I'm currently, in my copious spare time, working on a deep learning course with Keras. Enough said. Okay. Now let's look at what we're going to build. Remember those digits we looked at, the 8s and things like that? We're going to build one of those real quickly here. And we're going to build that using something called a convolutional neural network. Convnets, or convnets, whatever you pronounce them as, are perfect for looking at images and finding details in images, okay? And here's what they look like. No problem, right? Just knock that out, 5 seconds. Okay, well, that's what they look like. And what we have over here was we're going to take our digit, which is going to be, kind of ignore this 32 thing, we're going to remap it, a 28 by 28 pixel image, run it through there, And out the back end, it's going to figure out is that a 0, a 1, and what have you not. Okay, it's going to go through 2 stages, one called feature extraction. And let's see what that does. Oh, and how's it going to do that? Well, first it's going to kind of run this little block across each of the parts of the image and pick up information. So it's going to go scan, scan, scan. Then we're going to get to feature extraction. Got ahead of myself there. And it's going to extract features. Now, that probably doesn't look too good, and in real life, that's about as good as it gets. Because what we're trying to find are just basic features, like, hey, there's like this curvy thing up here. Oh, there's another curvy thing. Oh, here's some lines and things like that. Because then, if we can build up numbers from those lines. So we can take those various features, kind of abstract, put them together, and build up these representation of numbers. And notice how these are kind of like out of focus. What we want is a general representation of a number. We don't want to know that an 8 has a little thing that sticks up in the upper right, so that we have to reprogram it when the little thing sticks up in the upper left now. We just want this kind of general representation of numbers. Does that make sense? That's how we as kids actually learn this stuff, right? We kind of know what an 8 looks like, but we don't know precisely, we just know generally. Sir?
How do these images come about?
Okay.
First one, if not how, but more what are they, what we're looking at? Is it the same?
No. Next slide, and it'll become soon. Okay, how are we going to do that? Well, let's look at the implementation. First, as I said, we're going to scan through our thing, and the first thing we're going to do is run through what's called a convolution layer here. That's going to take these little 5x5 blocks, those little orange things we just saw a few minutes ago, and kind of run them across this number. Then we're going to do subsampling, which essentially means we're kind of squish those together. So those first 5x5 blocks, to your question, will be those little arcs and things that we have. And then we'll generalize them here with the subsampling. And in our code, we'll call subsampling pooling. So you'll see the word pool. So when you think pool, think what I'm doing is taking this bigger part of the image and squishing it down. Why am I squishing it down? Because you're going to pass it on to another layer that has its own 5x5 convolution and pooling. Let's get that out of the way. And that's going to then take those little arcs and things like that and kind of put them together, right? If you were to imagine you had an image and you kind of pull back and pull back and pull back. So you're starting to get the bigger and bigger picture of the number.
Sorry, I'm not understanding what
Convolution is just really just going through the pixels, reading all the values, and computing a value for each pixel, okay? And what we're going to do is kind of generalize those to get a trend type thing.
Do you end up with just one number for each 5x5?
Yes.
Just one value?
Mm-hmm. Don't go too deep into this. I don't want to. On CS 231 at Stanford, they have a great, it's a great course, and they actually put up huge lectures on details in this. I will tell you it's about 35 pages long, so don't get too hung up in the details of this. If you really want to deep dive into it, look at the Stanford CS 231, I believe is the class, on convolutional networks. The guy that developed convolutional network is named Jan LeCun, who happens to be the head of AI now at Facebook. Okay. And yeah, that's the 28 by 28. So let's take a look at code. All right. And we're going to have to zip through this, guys, because I am yammering away here too long. Mouse. Great. Something's going on here. Oops, I'm not getting a mouse. All right, let's switch. Oh, there it is. It was on that screen. All right, let's go over here. Sorry about this. Okay. Hide that. And now we have to hit Command F1. Can you guys see the code? Okay, cool. So rather than watch me try to type this, because I'll never get it right, I'm just going to pop comments off this. Sorry if that doesn't work for everybody. This is Python. We import the TensorFlow library at the top. And we also get our digits here from the MNIST library, okay? Now, let's take a look at some of this stuff here. I'm going to pop these first three things off here. Okay, first line is reading out of a data file, just loading up our data. So it's reading in data sets, and it's going to use the variable MNIST to represent those, an object called MNIST. Session, within TensorFlow, everything is run within the context of a session. And this lets you do things like shove my code over to the top of a GPU with a lot of cycles, or run on my laptop, or ship it up to the cloud. Same code, just point it to this location, that location, that location. Really nice, because you can debug in your laptop, ship up to the big machine, and just run against big data sets. Within TensorFlow, this placeholder bit down here, placeholders are just structures that are going to be replaced by user data. So every time we see X or Y bar, think, aha, that is going to be replaced in whatever equation I see with data fed in, with digits, our digits data, okay? Or in the case of Y bar, it's going to be fed in by what I think the proper value of that digit is. That's a 3, that's a 2, or what have you not. Okay, I'm going to skip this thing here because we're running out of time. This was just a dump so you could really see it was a 28 by 28 picture. And let's get down to the real code here. Okay, we're good programmers, right? What do good programmers do? Oop. Yeah, they code. But good programmers believe in dry, right? Dry, do not repeat yourself. So we have a series of functions here that are going to do a lot of work for us. You were asking about initialization. This is the initialization of our various variables. We're doing a truncated normal. Remember the old bell curve you learned in school? Truncated normal just lops the ends off and just jams everything closer around 0, or whatever the mean value is that you give it. You also asked about initialization of bias variables. These are going to get set to, I guess, 0.1 we're going to start with. Because we're going to be doing a bunch of convolution nets, we wrote a function here to do these and deal with some of the geometry we can pass in, like how wide things are and how big things are. Remember, they change size as we kind of went through. And we're going to do that. Okay, now let's see how we do this in code. The top of the thing, we declare our weight variables. These are n-dimensional arrays, that 5, 5, 1, 32. Remember the 5 by 5 block we talked about scanning through? We're going to have 32 of those 5 by 5 by 1 deep because we're using a grayscale image, right? 0 to 255. We have bias variables. We have 32 of those. The line in the center there is how we're going to create our convolution network. Remember we wrote the conv2d function at the top? We're going to call it. Somebody asked me about the activation function. That activation function is this one here, this ReLU bit here, right here. We're going to run through this. Then we're going to take the output, which is in this hconv thing, and then run through our 2 by 2 max pulling thing. Remember that from the diagram? Okay. Now, if I'm going fast, I apologize. We just have a little bit, we don't have much time. But once again, this is actually an example you can find on tensorflow.org if you want. Okay, they have one of these. Same data. Okay, remember we had 2 layers, though. This just gets us through our first layer, which is why I put 1 on the back of these things, so we can tell the first layer from the second layer. So we're going to do it again. Same deal, except now we're on layer 2. We define our weight variables and our bias variables. We go ahead then in here, create our second convolutional layer, and then our second max pull layer, and we're done. But then we have that fully connected layer we talked about. This is the one that lets us run through and then determine probabilities. Question?
How do you determine how many layers you need?
Yeah, that's kind of the dark or black art, shall we say, of these sort of things. In general, with convolutional networks, the bigger the image and the more features you're trying to get out, the more layers you have. You can kind of think of it, you remember how we were kind of getting generalized, getting small details and kind of using those to build up? Well, we're just doing digits. Can you imagine if you had a 4K image shot, right, and I want to pick out the little flower in the corner of the car? You're going to need a much bigger network, okay? All right, well, we're done with our two sets of convolution and pool layers. We're now going to do our fully connected layer, which is the one that's going to output our probabilities or help us output our probabilities. And I'm going to pop the, oh, come on. Ah, that works then. My mouse is working. Yay. I don't know who thought a trackpad was a good idea, but it wasn't me. But anyway, the fully connected layer that helps us output those things. Now the next layer, and I'm trying to finish this in about 10 minutes, so I apologize if I'm going fast, deals with an interesting problem. Neural networks are really, really good, all machine learning algorithms, but neural networks specifically, of getting into the little details. You know, if we let it, these things would go figure out all the little details, those nooks and crannies and things, those digits we looked at. But we don't want that. We want to generalize. So this dropout layer goes through and sets the value of some of the layers to 0. So that essentially just prevents them from contributing backward through our network. That detunes the network, desensitizes it to all those little gadgets and things like that, our little features. Okay, and then we have, finally, we have our readout layer. And that's the end of the layers. Now, all we've done is define structure in the world of TensorFlow. One of the things you do in TensorFlow is you define all these structures and things like that. If you hit the go button, nothing happens. Because all we've done is define procedurally how you're going to put the pieces together. You need to define a few more pieces, and I'll uncomment these. We need to define, for example, in a neural network, how do we deal with this dropout thing? That's what this thing does here. It essentially does a matrix multiplication of some values which zeroes them out. Second line, the cross entropy. Cross entropy determines how we figure out if you neuron thought this was a 4 and it's really an 8, that's an error. So we have to keep track of that, and this is how we do it. Now, the reason we keep track of that is the third line down there, the one that says Atom Optimizer up there, because what the optimizer does is say, hey, you know, this was an 8, you said it was a 4, that's not so good. So it kind of keeps track of that as to where it's going on, and then corrects those values, those weights and biases. It sort of tunes them to reduce that error. It does this over and over and over again as we pass more and more data through it, which is why having a lot of data for these neural networks is key. We're going to run this in a minute, and we'll see it does terrible when we first start out, but then it'll just start, you know, knee in the curve, accuracy will just shoot up. And speaking of accuracy, at the last two items determine whether what we said was there was correct, and how accurate are we in terms of a percentage. What's that?
What does the max pool layer do?
The max pool layer essentially takes a large set of layers and then abstracts their value, maps their values into a smaller space. Okay, so from a 5 by 5 matrix to a 2 by 2. Okay, so let's run the code. Then here, we'll just comment out the rest of everything so we can move right along. All right, scrolling back up here. Remember we said everything runs in the concept of a session. Anybody want to guess what this line here does?
Execute
Exactly, it initializes global variables. I mean, you know, you can kind of read it. TensorFlow, they're not afraid to spend a few, you know, characters to end up to be a little bit verbose. And I like that because I can't remember what x2 does. I can remember what globalized initial variables does. Okay. Here we import some things, and this just has more to do with setting parameters. We have a little loop down here, and we're going to time it. So here's our loop. If you're not familiar with Python here, Python uses indentation. No curly braces, no end fors or things like that. Indentation defines what's in the loop. So things indented 1 from the for are in the loop. Indented 2, still in the loop, maybe inside something else, like that if statement. So what are we doing? Well, right here, we're telling it, go and get the next batch images from the data, run it through the training step. Remember we said we had those placeholders, X and Y, and we were going to replace them with whatever we saw. Batch 0 is the image. Batch 1 is the actual value of it. So batch 1 has the pixels for that. Batch 0 has the pixels for that. Batch 1 has the actual number 8. Remember, keep probability, which was how many we were going to keep, is now 0.5. So we're only going to keep half the neurons in the network. Built that big old network, we're only going to keep half of them because it's so good at fitting the data. Okay. And because we would like to see this rather than waiting a week, maybe, you know, see it every once in a while. Every time the integer division of I goes to 0, we're going to display the accuracy just to see how the training accuracy is going along. Okay, so what we're going to see then is when we run this, we should see accuracy, you know, from 0, because 0 has a remainder of 0, is like really poor, like 20%. Then we should see it move up, okay, to 50%, and the next 100. And then at 200, maybe 80%, and things like that. And we should see this kind of ramping up pretty quick. Go ahead.
Is it cutting the number of neurons in half each iteration of the loop?
No. It is getting more data each iteration of the loop. And for each iteration of that loop, it is passing that 0.5 along. Because we only train that one digit in each iteration. Okay. Let me deal with that offline if you want. Okay. At the end of this, then, we're going to tell you how long it took. And down here, we're going to say, what is our final accuracy? And we always want to do a session close. If you don't, if you went up to Azure and had this push up to Azure, meanwhile, your bill is going higher and higher and higher and higher. And your boss is going to have a talk with you, and it's not going to be a pleasant talk. So do not forget to terminate the session at the end of the day. I'm using Microsoft Code, which is a really cool editor if you guys don't use that. We invoke Python by doing Python. And the cool thing is you can get this, like, you know, there's the thing running in the bottom. We don't need to go back to the code. In fact, let's just shove that up even higher. We'll let it run. Please, no syntax error.
So is your session occurring on your desktop, or are you setting this to the cloud right now?
No, it's running on my laptop.
Okay.
All right. So the first few lines you see there, it went in, great. Name error X. Where is X images? All right, sharp-eyed people, where is X images? Where did I do that? Was it 61? Man. Did I not comment something? Oh, hey. Group programming, great. No. This stuff had to do with just, was kind of a thing where I was going to print the thing. I'm pretty sure that's it. All right. Well, now you know what a TensorFlow error message looks like. You didn't know you were going to get that, huh? Okay. So it's running now. So what it did here is it pulled in the data at the top. That's what this extracting bit was. And then it always, TensorFlow tries to be helpful with you and tell you, oh, you know, had you like pulled down the sources and built it on your machine, it would have run faster. So it looks like it's blowing up, but it's really not. It's just trying to be helpful. So as you can see, the percentage of accuracy as we go on, after 100, we went from 6%, not too good, to 78% on the training data, now to 98. It tends to bounce around when you tend to get to the top, and it'll settle in. Curious to see, it changes almost every time as to where we end up at the final 600. And normally we'd run this for 3,000, but we'd run way, way too long if we did that. Okay, so it took us 51 seconds to do that, and my fan is spinning up because we really overheated the machine, and we were 95% accurate, which is not too bad for just a few lines of code. So is that good enough? That's a good question. If it's, you know, you, me, or anybody else guessing a number, we have a 1 out of 10 chance, so 10% accuracy. Much better than that. If we're developing the system for the postal system, not so good. Okay? All right. So let's just finish up with a couple of slides. I'm going to actually zip past these here. These are just some things we can do with that and kind of get to, oh, I know. I know what the problem is. Wow, this thing is like super heating up on me here. Can you hear it? Yeah. Okay, so anyway, you can do certain things with this. Obviously, with images, you can do security, iPhone X, right? Product inspection. You can work with text, find things, find the real sentiment, this sort of thing. You can do translation, machine translation with these. Google Translate does that. I'm going to hold all questions till we're done because I'm eating into the next guy's time. And I'll be happy to stand out there as long as you guys want to talk to me. Interesting to note, we're getting very, very close. Actually, I talked to some guys at Google who say they are now exceeding in certain languages the ability to translate beyond human capability. Okay? And one of my favorite tools, everybody use Google Translate on your phone and things like that. If you ever travel internationally, great. Not the Star Trek Universal Translator, but darn close. Let me leave you with one last quote. AI is the future. Somebody, not a computer scientist, gave this quote recently. Any thoughts as to who this was? And who?
Jeff Bezos.
No? Somebody a little more powerful than Jeff Bezos. He gave this at a starting session of, you know, to the freshmen, if you will, at some sort of university in Russia. So this just goes to show you where AI, deep learning, and all that is now perceived all the way through the pipeline. And with that, I'm done. So.